We have a great speaker for today, and Kamazima has the honor to introduce our speaker. You can come here to the front too, then people can actually see you in the
on the Zoom.
on the Zoom.
Yes. Good morning. I'm Kamazima Louisa. I'm hosting Dr. Jim O'Donnell from UConn. I've known Jim for the last 32 years. And he used to beat me at playing soccer. I don't think either, he's still playing. I can't play anymore. My knees can't move. So Jim got his bachelor's from South Carolina. I didn't know that. I thought you went to Cambridge, only.
Yeah, I put that on my resume.
And then he did his master's and the PhD at the University of Delaware. This must have been under government, right? And so he's worked a lot in Long Island Sound, and that's where our paths kind of crossed a lot. And he's been the chair of the Long Island Sound Study Technical and Advisory Committee. And that was for
a decade.
Quite a 10 years. Long. That's how long you expect me to stay.
Yeah, once you get in, it's hard to get out.
And so today, I invited Jim, and I thought he was going to be talking about physics. And he said, "Oh, I want to talk about the O18." I said, "What's that?" So I don't know what that is, but I invite you to listen. I'm also very, very eager to know what that is. Jim, welcome.
Well, thank you. It's a great pleasure and honor to be here again. As Kamazima said, I don't live very far away, and I've been here many, many times. And one of the first seminars I gave as an assistant professor was here in 1987 or so. And so some of you may not have been alive then, I'm sure, which I regret. It was a great time, I'm sure. And as Kamazima said, I'm a physicist originally and a theoretician, actually. But since I've been at UConn, I've evolved, and I'm much more highly funded and spend most of my time now looking at data and very little doing what theoretical work myself. But this one we're talking about today, a model for delta O18 ratio structure in Long Island Sound, I did pretty much by myself. You know, and for a senior full professor, it's unusual. You do get to actually work on something interesting. I hope it's interesting to you too. And I know there are some real geochemists around, and so I'm going to try and not be wrong too much, but I think the mathematics is correct, but the language I might use is maybe a little unclear. Also, I have a funny accent still, though I've been in the United States for 40 years, more actually, most of my adult life. I'm from Scotland. That's why I went to the University of Strathclyde in Glasgow. And if you don't understand what I say, you know, put your hand up and I'll try and say it again with a better American accent.
I'll translate.
Okay, yeah, we'll try that. So the talks have two parts. The first part's about Long Island Sound and the hypoxia problem, and I've got a little hang up about that. I'll try and explain. And the graphic on the left here, this shows the wastewater treatment plant loading over the last 30 years in Long Island Sound. This aggregation of all of the discharges around the East River, more or less. And this is the area of hypoxia. And what you see, you know, is that there's like a trend, and there's error bars on this that I'll talk about in a minute. But this is the point that there are 4 or 5 years which are distinctly different from the rest of it. And that's sort of the first bottom line is that the goal of the management program that was started here actually, you know, negotiated as a settlement between the city of New York, the state of New York, the state of Connecticut, and the EPA. The New Yorkers and Connecticut people had to spend a few $1 billion to upgrade water treatment plants to reduce the area of hypoxia from like what it was early in the late 70s, early 80s to what it is now. And the goal was about 200 square kilometers. It used miles, but I converted. And then the program decided how to do that was kind of negotiated between people, including scientists, Don Pritchard, and was here, and Frank Boland was a Connecticut representative, and they wrote a report in which they laid out. I read it actually recently. You know, they laid out where the stations would be and how we would make the measurements and stuff. And I'm going to show you the results of that. 40 years later. So because I don't get all the way to the end, here are the results. 80% of the years looking forward, we should expect that the goal to have been achieved, and there's 20% of the years, 1 in 5, where it might not be achieved, and we don't really know why. That's if current loads are sustained. In bad years, the area could be up to about 500 square kilometers. In the good years, it should be down about 200. Now, what causes variability and what causes hypoxia? That's been a subject of debate for the last 30 years too, and there's been modeling efforts associated with trying to understand how nutrient load would impact hypoxia area. And there's controversy about about how it works. And so I worked on a model for the vertical structure of the distribution of delta O18, which is a ratio, 1 minus the ratio of the O18 isotope to the O16 isotope in dissolved oxygen, and times 1,000, right? And I'm not quite sure how it's measured. My colleagues that I acknowledged in the title here, Mark Altabet and Craig Tobias, they made all those, and their students took the water samples and made the measurements. And I just did the mathematics and interpretation. And I'll talk about that in more detail. But the bottom line of that is that much as I tried at their insistence, that the effects of benthic oxygen demand during a period of hypoxia, at least, is modest, very modest. Most of the oxygen that's been produced in the phoric zone in Western Long Island Sound in the summer is respired or degassed to the atmosphere. And that's the conclusion of all this mathematics I'm going to show you later. Okay, so most people I talk to know about Long Island Sound, and I see you've got a nice map up here. This is the first map I found, a nice leveled map, so I thought I'd show you that. But the quite important data there was made in 1674. So people have lived around this area for longer than that, obviously. But since 1674, the colonial period and the development since then has changed Long Island Sound dramatically. This map is not accurate in detail, but one important difference between then and now is that this little stretch over here, the East River, has been dredged and narrowed, so it's deeper. And so the connections for exchange between the mouth of the Hudson and the western part of Long Island Sound has increased. And the water treatment plants for all the people that live around this area now, maybe like between 10 and 20 million, depending on how you count. Much of those discharges occur in this part of the Western Sound, and the mean flow, although the mean flow, the vertically averaged velocity, time averaged over a year, goes to the west. There is a flux of fresh water to the east. Now that's because it's called dispersion, but basically water moves back and forth like this due to the tides. Now, although the mean flow goes that way all the time, on each tidal cycle, some fresh water at the surface goes to the west, and that mixes vertically and horizontally. And then the water that comes back is slightly saltier. So that mechanism of sloshing back and forth, together with mixing vertically and horizontally, leads to a net transport of fresh water to the west, to the east, to the east. Although the mean flows to the west, fresh water goes to the east, and that leads to lower salinity here than over here. Right? And that's unambiguous. It's hard to measure directly, because it's. And I've been trying to do that with. I've done a lot of measurements to try and resolve that. and understand what controls the variability for reasons I'll get back to. This is a modern map, and it shows that the topography, and most of this topography, you know, the red and yellow, that's natural. There's very little navigation-driven dredging in the middle of Island Sound, and there's been some reef planting and stuff, but most of the dredging has occurred here, and then in the harbors and estuaries, and there's some deposition of dead materials, but it doesn't really affect the circulation on a big scale. But the thing I want to emphasize here is it's deeper over here, about 40 meters in this area. It's largely like 20 meters here. And there's sort of a deep channel. It's a relic channel of the drainage when this was a lake. It's a fascinating story. I don't have time to belabor. And the currents are pretty strong in the east. These are from measurements of current meters I did a long time ago. And this scale is 25 centimeters. So the currents here were about plus or minus 60 centimeters per second. But in the western part of Island Sound, 25 centimeters per second is this arrow. So this here is about 25. Right. So currents are sluggish in the west, and that's well known why, because of the friction and the shape of the channel, and it's nearly a quarter wave resonator. And physics of that were Larry Swanson actually did the first models that explained this structure. And most of the river discharge into the sound itself come through directly from the Connecticut River. And this is the seasonality of the river. In the spring, it averages about 1,500 cubic meters per second. And it's for those 3 months, it's above average. The rest of the year, it's below average generally. And the annual average is about 500 cubic meters per second. And that's about the same as the Hudson. But the Hudson enters the sound through the East River. And so we don't know exactly how much of that water gets into the Western Sound. We have to infer it from looking at salinity distributions. So this is a map. There's quite a lot too much on here, of course, because this is from a review paper that I led a decade ago now, nearly, in which we tried to solve the physical oceanography of Island Sound, right? But in it, I was trying to accumulate to describe what the structure of the hydrography was. These red and diamonds and yellow diamonds, they are the survey locations that the Connecticut DEP has been sampling monthly throughout the year and bi-weekly in the summer since about 1980 or so. And the initial survey locations were fewer because they were starting up. But the goal was to try and understand the extent of hypoxia in the Western Sound. There had been sort of anecdotal descriptions of dead fish and smelly water close to shore, etc. And the survey programs initially was done with bottles. This was much as that. It doesn't. It's for me, it doesn't seem like long ago. I was a graduate student in those days, right? But sampling was hard. I worked on the first Neil Brown CTD as a graduate student in 1981, programming the data logger. And before that, there was no direct measurements of depth, etc. You got a thing over the side. It was pretty primitive. And that's what the early measurements started out being like. And then Pritchard and Swanson and Bowen and EPA kind of had a meeting here, and they picked these stations and they said, we're going to try and do this every month and twice a week in the summer so we can understand the spatial extent and the variability. And it's one of the biggest and longest lasting surveys of estuaries anywhere I'm aware of. And I've done some other things, like looking at lateral variability. It turns out not to be very big, but I published it and got tenure. This is the analysis of the evolution. So I'm going to show you the seasonal cycle. So who hasn't seen this before? Like the evolution of Island Sound hydrography. Is it news or okay? At least two people will learn something. So in the summer, this is April, August, and December, and this is a cross section down the middle of Island Sound of salinity. And the important part is that it's saltier over here in the east, where the Connecticut River enters, right? And it's fresher over here in the west, where the Hudson influxes salinity. So it looks like an estuary, but it's kind of unusual right? And the fact that the river's on at the ocean end. And but that water mixes into the sound here, largely over the sill at the western part where I showed you the currents were strong. But then it slowly drifts to the west, and it mixes with the water near the surface, which is fresher. So this gets fresher as you go west, and the freshest water comes from the Hudson, even though the mean flow is going to the west. Right? So averaged vertically and horizontally, and over time, water is moving this way, but the salt is going that way. That's kind of unusual. The other interesting thing is that the isolines, and this is the average of all the April surveys for 30 years, right? Roughly. And this is all the August surveys for 30 years, and this is all the December surveys for 30 years. And there's well, like 10 stations along this section. I just put in these 4 to illustrate where we were. So this is a Hypoxia region. And in the winter, notice the isohalines are almost vertical, and that's reflected in the temperature too. In the spring, in the winter, it's cold. In December, it's uniform temperature, and it's like between 2 and 3. Very cold. And in the summer, the temperature at the surface can be like 22, 24, 26. Depending where you are. So the temperature range in Long Island Sound swings 25 degrees. And that's another kind of unusual thing in Long Island. It's one of the most variable in terms of temperature in the world. The other thing that happens is it's very stratified in temperature in the late summer, in August. But then in October, right about now, cooling begins. And the cooling cools the surface water and it sinks. And so there's this, and then the temperature becomes almost uniform vertically, even though it's stratified in salinity, as I showed you. Right, so this is an interesting and complicated thing that students often and professors often don't get. Right, how you can have stratification and salinity but homogeneous temperature, and it's because of a mechanism called SIPS, these shear induced stratification. So water is constantly going like this, right? So if it's fresh over here and salty over here, circulation like that will create stratification in salt, right? And then but mixing occurs in it, and it homogenizes it. Because there's no horizontal temperature gradient, or very small horizontal temperature gradient, the rate of restratification of temperature is weak. Because a strong horizontal salinity gradient, the rate of restratification of salinity is higher. And so mixing will homogenize both, but the rate of restratification for salinity is higher because the horizontal gradients are higher. Right? And so I have a nice paper in which I describe I make measurements of the heat evolution in the fall, and using data and models recently describes this. Now I'm going to skip the density because it's basically stratified in the summer. Right, August it's stratified, and in the fall, its stratification and density is much weaker. Oh, I'm missing one. That's weird. So this is the hypoxia problem. And this one here is the spring, which is summer disappeared. July, August, and September. Now, and the concentration is in milligrams per liter. So in the winter, September is when after the cooling has started, it gets much more less stratified and less stratified in oxygen in the east. And there's still some residual vertical variation in September, that's right now, because there's high respiration rate still. There's mixing, but there's still high respiration rate in the water column because of it's still warm in September. But the highest gradients and the lowest oxygen at the bottom occur in late August. You see over here that this is a 3 milligram per liter, and again, this is the 30-year average August oxygen concentration. And it's below 5, which is substantial oxygen reduction across at least half of the western part of Long Island Sound and the bottom half of the water column. So it's not just that the bottom is near hypoxic over in this little bit over here, is there's oxygen sag everywhere in this western half of the sound. And it's been like that since measurements have been available. So, but here's one of the innovations that I brought in 19 I guess it was 1990 or so. No, 95. I think we Bolin and I, Frank Bolin, a collaborator at UConn, who's since retired, and I wrote some proposals to put buoys in Long Island Sound to measure the evolution over time. Because prior to this, though we have a great data set, and all of the EPA managers keep asking why do we need to make measurements, because we've got so much data, right, about Long Island Sound. It's twice a week. Seems like a lot for a ship survey, but when you look at the variability, it doesn't resolve it, and that's what buoys show you. So this is the results from 3 buoys. And I maintain 4 at the moment. One over here too, but this is called the Central Sound. What I call execution rocks, Western Long Island Sound, and Archie, which is named after a guy who was a pain for me, but he passed away, and he was a big. His name is Art Locke, and he was a big supporter of the Long Island Sound study, though he was very critical of scientists in general. So this is supported by EPA, and this is supported by NOAA, and they have been for over 20 years. And it's a lot of effort to get this. I don't want to diminish that, but I don't want to talk about it too much. What I want to show you is that there are periods, although the oxygen starts near saturation in the spring, and it decreases fairly quickly to low values. This is 2 again here, this is 1. And the green is execution rocks, which is the Western Sound, farthest west. Ship surveys show this decline. They don't show these intermittent occurrences of increases. And then late 90s, I didn't know anything about oxygen. I as a physicist, worked on circulation models and mathematics. A friend who's a geochemist, Tom Torgerson, who's at UConn, he brought me this issue that he had been worried about. If you look at if you take water samples, in a bottle, and you measure the rate of respiration, the rate of oxygen loss from that bottle, you find that the rate is about something like 1 milligram per liter per day, right? If you look at this trend from here to here, it's like this is like 100 days, and that's like 10, so it's like 1/10 of a milligram per liter per day. So he said, how can it be that this bottom water, which at the time people thought was so isolated from the surface, and was going hypoxic because of lack of mixing due to thermal stratification, how could it be that the water samples show 10 times more respiration rate than the long-term trend, right? But then when you look at the data from a ship survey, and you sort of smooth it, what you see is that there are periods where the rate of oxygen decline is really rapid, right? Followed by periods where it goes up again. And so the long-term decay in oxygen, the 10 per over 100 days in a rate, is the consequence of rapid respiration at 1 milligram per liter per day, followed by some ventilation of oxygen injection into the bottom, right? And that's going to include me into the complexity of this problem, and why mixing and circulation was really needed to be understood in order to understand the variability, the causes and the variability in hypoxia. And so all 3 buoys show that, and every year since then they kind of show that. And I'm going to come back to that in a moment. Now, the thing that's regulated through the agreement that was made by the states and the city and EPA is the area of the bottom of the Long Island Sound that is hypoxic, right? And the Clean Water Act requires that once a state that deems an area is impacted, that they take action to mitigate the impact, and that was what this consent agreement was about. That shows so the thing they could measure easier at the time was the area of hypoxia at the bottom, because you only had to take a sample at the bottom and measure it there. And the CTDs were not easy with DO sensors. An automatic recording DO sensor was not available and not reliable really until about 15 years ago. And so water samples with Winkler titations, etc., was the way people did it, and it was laborious and time consuming. And you could do 3 or 4 at each of these stations, but that's a lot of stations to do that. So this is a map, and the red here shows less than 2 milligrams per liter. This is 2 to 3 milligrams per liter. This is 3 to 3.5, 3.5 to 4.8. Right? And so you see, and now the state at the time, New York deemed hypoxia to be, I think it was 3.5 milligrams per liter, and Connecticut deemed it to be 2 milligrams per liter, or vice versa. I've forgotten which. And so the legal responsibility then was a little ambiguous for a while. What is hypoxia and how big is it? It depends upon what your threshold is. Right? But nevertheless, this was one of the worst years where the area was extensive, and it was less than 3 from all along here. And notice it's sort of asymmetric. This is a thing I didn't quite get until recently. Now, when the first in the early years, like in 1978, 79, when Barbara Welsh and John who at Stony Brook there was one person from Stony Brook got some money, and one person from UConn got some money. And of course, they were supposed to collaborate, and it was difficult, but so I think these are UConn stations, and there was 5. And so the presumption was that, that variation occurred along the estuary, and they just sampled 5 stations, and that was where the money went. That was what they could afford at the time they had, and the technology they had. Notice over here, I've put, and this was a map they got for hypoxia. So this color again is like 3.5. So this area here would be less than 3. You can count it up. This is 100 square kilometers, this box. So that would be like 300 or 400 square kilometers. Now, obviously, if you have only 5 samples, you can't make a map like that, right? And but after a few 20, 30 years, you can start making trend analysis. Now, the way that the area was computed was that they take these sample locations, but found the lowest value in each profile, and then did an interpolation to the whole bottom of Long Island Sound using inverse distance weighting interpolation. Right? And now, when they first started doing it, I was at UConn. Remember, it was 81 or 82, and that someone in the geography department had gotten like a Sun Microsystems workstation with a color monitor and a primitive GIS application. And that person was the one who decided how to do the area interpolation. And I think she was a geologist. And so then that process is what they've used ever since. Now, at the time, it started out with data like this. That was this in this map. It was hand contoured by the husband of a lady who was a PI, and he was a seaman of some type. So it wasn't really very rigid, very rigorous in the scientific because of the technology available. And then, but more recently, they're using the same GIS application to analyze this data, and they redid this map. You still have to make assumptions about what the lateral variations is. So the point of this comparison is to show that if you've got higher resolution data, you can make a more precise estimate of the bottom of the area, right? Than you could if you've got fewer stations. So the uncertainty estimate around the area of the early stations, the early surveys, has to be much bigger than the uncertainty estimate later. And this is like confounds some all climate trend analysis, right? The temperature measurements from the 17th century in the Pacific are got to be treated with a lot of uncertainty relative to the ones that we make now. So that's one challenge in analyzing long-term trends. And I addressed that. I'm going to show you. And the other one is that even if you do sample every 2 weeks, and this is an example of a buoy record from, I think it's the Art G buoy. northwestern sound buoy in 2005. And what you see is these are the dates on which the ship surveys went out. And so if you were there, those surveys were, these profiles were obtained a day before or a day later, right? The oxygen level would be different. And if they were a few kilometers apart from where they were, if the ship was not as precisely navigated as you would like, there would be an error in that too. So those errors or that variability in the field, that leads to an uncertainty in the area estimate as well. And so I try to build that into my analysis too. So the way I did the area calculations, I interpolated the same way they do. I just did it automatically with the MATLAB application, and then with the same data set, I subsampled it. I said, what would you get if you only used these stations? Right? If you map this data, but only using these stations, you get something like that. Right? And I did that for a whole bunch of all the surveys that we have. And there's one a month for 30 years, right? So I can estimate what the uncertainty is in the array bias, it's called the array bias, right? By subsampling high resolution surveys and estimating what the difference is in the area that you would get if you'd used low number of samples. So I've done that. And then the other thing that's sort of innovative is that you should expect a linear trend in the area, right? Because the model that was sort of adopted early on was that the area would be reduced if you reduce the nutrient discharge, right? So the hypothesis has always been that eutrophication leads to hypoxia, and if you reduce the level of nutrient load, you should reduce the area of hypoxia. And this is because the seasonal average nitrogen discharge from water treatment plants by management zone. So these are all the management zones that were defined. I live over here, right? And they did this to try and assign how much investment each area had to impose on their taxpayers. Right? The idea was that everybody's got to upgrade their water treatment plants, but these people over here, they've got to do more because they impact this area more. And there was a model argument for that. But this just shows what happened. So in this is 85, roughly when things started, and then there was nothing. So it takes a long time to motivate politicians to change budgets, etc. And then it takes time to actually implement projects and water treatment plants, I suppose. So nothing happened until 95. Then there was a deployment of some technology, and things got better. This is this area over here. And they have the biggest loads. And then I think the loads have increased again. And then there was another technology innovation in 2010, and things went down, rapidly down from there too. So you might expect that the area of hypoxia should be related to that nutrient load trend. So this is the data out to 2020. I have it now to 2023 actually, but I haven't updated this. I got the 2023 data earlier this week. So these are the early years when they were doing the coarse sampling array. Here's like 2000 or so, and then there's 2000. So once people started seeing data like this, like imagine you were Long Island Sound Management Committee meeting in 2000, right? And you had this data, right? And you'd say, well, are things changing? We've invested $1 billion, right? And nothing. And so people were kind of nervous. Then by 2010, now we had this, right? And this red line I drew on it, but people were drawing lines on this at the time, and squinting and saying, yep, it's getting better, we've got to do more. In fact, it's still, one of the interesting things about the Clean Water Act is it empowers private citizens to sue governments and other polluters to upgrade and to stop what they're doing. And so even now there are threats from NGOs to sue the city of New York to reduce their nutrient load further. So this kind of analysis is an important practical application. It's important practically for society broadly, and everybody who pays taxes, and everyone who cares about the environment. So the first thing I did is what everybody else did. I put a line to this, and it's easy to do. But then I also looked at the residuals. That is a difference between these samples and the fit of the straight line. And the first point that's important is that notice that there's all these ones are negative, then there's a bunch of positive ones and a bunch of negative ones. They're not random. And if you remember freshman statistics, right, the assumption of this linear regression stuff and the hypothesis and testing arguments presume that the errors are normal and that they're random and they're uncorrelated, and these are not. And that's what this shows too. So, so what do you do? Well, first you need to have an estimate of the uncertainty in the area estimate, right? And I showed you how I computed the array bias in the early stations because of low density. But even when it's high sampling density or higher sampling density, there's still errors associated with this variability, right? This is a Buoy records show this variability. So I can quantify what that is by calculating the standard deviation around 2-week chunks, right? The idea being that the standard deviation around 2-week chunks in a Buoy record is roughly the uncertainty you should apply to a sample that you take once every 2 weeks, right? Then you can propagate that through the area calculation using Monte Carlo simulation. So my program takes the data, calculates the area, and then I add to each sample a random number with a standard deviation computed from the 2-week standard deviation of these records, and then calculate the area again. Now the buoys are slightly different. The standard deviation at extreme rocks is about 0.6, about 0.3 at the Western Sound buoy, and about 0.15 at the G buoy. And there's plausible explanations for why that is, right? And I want time to tell you about. So I just prescribed the standard deviation pattern for all the data samples, and what you do out here doesn't really matter. I tested that. But these numbers, and it's not too sensitive to these, so long as you acknowledge that it's big on the extrusion rock side. And then you can make so you calculate 10,000 areas for each survey. And the idea being that each of those replicates is consistent with the sample that you got, plus the uncertainty that you estimate, right? So then you calculate the standard deviation of the areas for each year. And when you do that, I'll skip that. I'll show you this. This is what the time series looks like. Now, these are the uncertainties. Notice the ones here are really big, right? They're because the sampling array was sparse. They're big here because once the 2 or 3 contour gets to the east, the sampling density, the array density is sparser in the east. And so the resolution of the estimate of the area is coarser. And as the area gets smaller, the sample station spacing is tighter. I don't know if they planned that, but that's what he did, right? And it works out that you've got a better estimate of the area when the area is small because the density of spacing of the samples is higher. And so you do that, you can do the same fit thing, but now you can use this, and this red line, I think, is the simple regression, the naive regression, the one that doesn't appreciate the errors. Then you can weight the ones with you weight the samples which are very uncertain low, a weighted order of least squares, and that's sort of a rational thing to do. If you're uncertain about it, you weight it low. If you're certain about it, you weight it high, right? And you build that into this least squares regression process, and you get the blue line. But then when you do that, you see that these points up here and the errors are radically different from the rest. They're absolutely inconsistent with the notion that there's a linear regression in time here. And if you look at the residuals, you can also see that they're still pretty correlated. But remember, the hypothesis, though, was that it should be controlled by the nutrient loading. So when you plot it against nutrient loading, what you see is like most of the years follow this cluster here, and these red and purple lines are the purple line is the least squares fit for all the data. And the red lines are the fit for excluding these anomalous points. So we've got 30 years of data. 25 of them are consistent with a linear trend proportional to the nutrient discharge. And they're consistent on all the statistical measures that you want to have, like those chi-square fitting and stuff like that, which I won't worry about, right? But it's like, but it's freshman stats. If you read the last chapter in the freshman books about chi-square fitting and analysis of variance and stuff. Now these years are anomalous, and we don't know why. I don't know anyway. Now you can do the same with other. So that was about the 3 milligram per liter contour, and you can do the same with other contours. You know, and different contours have different uncertainties because, like a higher contour goes further east, right? And so the area is less well resolved there, and so the uncertainty is bigger. And so these are another thing you can do, which it's not. I was obligated to do because of contracting. But it wasn't very interesting. It's to calculate the hypoxic volume. So in addition to looking at the area, you can look at the thickness of the layer that is below 3 and calculate the volume that's below 3 or 4 or 5, right? And this shows that I did it, right? But basically, and there's a trend, and you can show that it's significant if you calculate the uncertainty in it too. But the bottom line is this, right? That there is 80% of the years, nutrient reduction has worked. 20% of the years, it hasn't worked. And going forward, so long as we don't increase nutrient loading, we should expect that the management plan goal has been achieved. Except for these 20% of years where it's bad, right? And we need to figure out why that's true. So that requires better understanding of the mechanisms that are responsible for the variability. I think the nutrient loading question about the general process is right. So one hypothesis that one of my colleagues, several people have done this, I guess, is to exploit the fact that phytoplankton prefer, the smaller oxygen molecule, oxygen atom, right? O16 to the bigger one. And so the process of production tends to of oxygen tends to concentrate change the ratio from what it is in the deep ocean and what it is in the atmosphere through this isotopic concentration process. And then respiration also changes it. So there's respiration in the water column changes the isotopic composition as well. We don't think any of the process, this is the idea of a model, that there's oxygen coming through the surface of the ocean. And this is like a small sliver of the western sound where it's hypoxic in the summer. That's what I'm going to look at. I'm thinking about what happens in August during hypoxia. What are the processes that control the rate of respiration in the oxygen structure? There's gas exchange at the surface. There's production by phytoplankton at the surface. Then throughout the water column, there's respiration by bacteria and largely. And then there's material in the bottom that's oxidizing chemically and organic, and there's bacteria doing stuff too. So there's a benthic demand. So oxygen is flowing into the layer which is like close to the bed and the bed too. So that's the simplest sort of idea of hypoxia. It's like when this respiration is higher than the mixing, oxygen goes down. And so how do those processes, or the rates of those processes, modify the ratio of O18 to O16? That was like the question my friends asked me. So the first thing I do is get a model, and this is a time-dependent, one-dimensional model of the oxygen concentration C. Right, that would be for the total oxygen or the big component, the O16. And there's rate of change is equal to the production minus the respiration rate. That's the constant times the concentration of oxygen. And then these two things are vertical mixing. This is the vertical mixing times the second derivative of the gradient of the concentration. And then this product is the vertical variation of the mixing coefficient AC. The last term isn't really too important, but it's physics, so we know about it. I had to include it. Now for the bigger oxygen atom, all the terms are the same. There's the mixing coefficient, the respiration, but these coefficients modulate. They're the isotopic fractionation coefficients. They're the rate at which the bigger one is processed. Mixing has no fractionation. Here we've got production and respiration, and we've got coefficients that people can measure in the labs. And then we need boundary conditions. Right, this is the boundary condition at the bottom. It says that the oxygen 16 is a flux to the bed. It's proportional to the flux in the water column has to go into the bed. So the demand by the bed is B, and the flux is this. It's a mixing rate, the mixing flux of oxygen towards the bed. So the mixing flux towards the bed, near the bed, has to be equal to the demand by the sediment. That's what I said. And the same is true for the bigger isotope, O18. But in this B thing it can't be positive when there's no oxygen there. Otherwise, the concentration of oxygen would go negative when we go on that. So I restrict B to be 0 when the oxygen goes to 0, but otherwise B is a constant which I prescribe. At the surface, there's gas exchange. So this is a traditional gas exchange coefficient. And there, the gas exchange through the surface is proportional to the difference between the saturation concentration in the water and the concentration in the water, and that has to be equal to the mixing flux. So anything that comes through the surface has to get mixed away. That's what that comes. And then there's a fractionation in that. And what gets mixed into the ocean has got the isotopic ratio of the atmosphere. So I did chemistry in high school. I took a one semester class when I was in graduate school. For a 1 semester, 1 credit class. So this took me like 2 weeks, like I said. And that was just writing the equations. Now I've got a bunch of parameters to choose. Let me summarize. The red ones are how production works, what the respiration rate is, what the mixing rate is. These coefficients, my colleagues told me. So there's there've been measurements of demand recently by some old ones when it was harder, but these ones are from a student. This is the FOD. That would be the flux into the bed. And then these are water column measurements, and there's lots of scatter. And these circles are bottle samples over a period of like a couple of years over a bunch of different stations. And this thing here is my estimates from looking at buoy records. So there's vertical structure that's clear. I think that's other places show that respiration is proportional to production because there's more stuff where there's production. And so I've got to pick a value though, and I'll show you that. And so I prescribe it to be exponential with depth. A couple of coefficients that look roughly make it look like this, which is roughly like the data. It's not inconsistent with it anyway. And then I looked at the literature for values of the benthic coefficients, and I got those. And this is I run the model, and I'll tell you a bit about it. But then this is actually what the respiration rate is. It's the coefficient times the value, right? So it varies. And so doing the steady state condition in my model, this blue line is what the model says respiration rate is. And I'm not going to tell you about the F statistic or the goodness of fit in that, but it doesn't look too bad. And the production is varies during the day, and I've got values that are based on measurements that our Kremer did too. And then the time variability comes from a formula by Pachitano. And this is very, and I compared this to observations I made, and it's not too bad. And I'll show you, and then I have to pick some eddy diffusion coefficients, and this is the thing I've been working on a lot recently. This shape, it prescribes AZ, it's big in the boundary layer, and it's weak in the middle, and it's high at the surface, and it's unsteady, and it's variable in time. And I'm working, and I deployed 5 beam ADCPs in the Western Sound to measure the dissipation rate, from which you can infer what the eddy fluxes are. But my program's still not working properly, so I'm just going to show you this. And I'm also working on a version of a 1D turbulence model Gotham that I will use to compute AZ better. But it's going to look something like that. And you have to formulate it as a finite difference scheme to calculate it. So you prescribe initially some arbitrary distribution, specify the coefficients, and let it evolve to a steady state. And this is what you get for oxygen. Total oxygen, this is O18. And then this is how this black line is where I prescribe the starting points. And after a while, it gets to this steady state. And this is the delta O18 ratio structure. And you see it's like low at the surface, higher at the bottom, because the mixing and the production actually pushes it down. And this is how it evolves pretty quickly. Things at the surface, it becomes periodic, after like 5 days. At the bottom, it gets to be almost as constant after like 10 to 15 days. So that's just characteristics of what these ratios look like. And these are using my best estimates of the parameters. And from the solution, then you can compute that in the steady state what the fluxes are. Right? Here is the integrated production in the top meter or so of the water column. This is the integrated respiration from the bottom to the surface. This is the flux to the atmosphere, and this is the flux to the sediment. Right, and this is another interconnect. And in the steady state with these assumptions, these parameters that look plausible, and the oxygen structure looks plausible, the sediment demand is really small. And it's didn't have to work out that way. And I can look at some sense, and this is the effects. This is how with those parameter choices for 2 different cruises, this is how the delta O18 ratio data compares to the model. So this is dissolved oxygen predicted, and this is the black line is the delta O18 ratio predicted, and this is the model results. Sorry, this is the data, and there's a bunch of different depths. And so, yeah, that looks, not too bad. And this is that's why I showed you those fluxes, because these are my best estimate at the moment. So then I can double in half the production rate, right? Because I picked a clear sky irradiance and a production rate that was roughly right. I could double it, and that pushes the solution from the black line to the red line. And if I half it, it goes from the black line to the blue line. Right? And those are much less consistent with the delta O18 ratio results. And the budget doesn't change too much. But if I change the mixing coefficient by 5 or 10, right, it increases the sediment demand, because what you're doing is mixing more oxygen down to the bottom, and so the oxygen benthic demand can use it. When there's no oxygen, can't be any benthic demand, right? So mixing and respiration in the water column limit the flux of oxygen to the bed, and so during the height of the hypoxia season, it can't have much effect. At least that's the conclusion I have here. So that's it. We got 2 minutes for questions, I think. Yeah, I'm going to make a break for it.
Now we can see.
Don't all rush at once.
I'll start. So going back to the sediment demand, for a long while we've had this idea that sediment can absorb 20%, but your results seem to be contradicting that.
Well, my analysis earlier was that it couldn't be bigger than 20%. Right? And what I've shown here is that in the deepest part of the hypoxic season, like in late August, there's no oxygen there, right? There's not much flux. Doesn't mean, and this model is a time integrated thing. right? So I could, in principle, simulate the evolution from early stages, May through August, right? And if you did that and you integrated the net effect of benthic demand over the whole season, the conclusion might be different, right? But clearly, I've always I've wondered about this. Well, let me add one other thing, one other point of evidence that unpublished and incomplete. Nevertheless, it's not inconsistent with what I'm arguing here. We built a sediment flux device with a turbulent velocity probe and a high frequency oxygen sample and deployed it in Westward Sound. And we couldn't get any oxygen flux because it was too low. Right, and the noise level and the instrument's performance requires that you can only resolve fluxes that are like 50 millimoles per meter squared per day, and so it's less than that. So and then we deployed it, in elsewhere. We got bigger numbers as other people have done this other places have found. So it's low. It's definitely low in the late summer. Doesn't mean that it's not unimportant in June, July, and August, or even and then in October. We find in October, November, when the water is warmer still, and there's a lot of organic matter around, and now oxygen is getting mixed down through this cooling-driven convection process. So, the more benthic demand, and it's not going to. The reason this is important for those who haven't been following the line on side modeling drama, is that the model that was developed for the EPA it was called SWAM, couldn't get hypoxia, right? And so they did some fudges. They reduced the vertical mixing in the model to get hypoxia, but they spent a lot of time wondering whether or not the problem was not enough benthic demand, and that drove people's thinking for a long time. And now there's a new model being developed, and the question is like, how much benthic demand is occurring? And it may be that the transition from June to August, that makes a difference, because what you see in August is the result of what's happened, right? It's integral over time of the demand. But we haven't, I haven't got to that yet, and I'm not sure this simple model that I've done, right, which is very rewarding. Pat myself on the back for still being able to do that. But it's maybe too simple because it doesn't have the effective advection, horizontal advection, and that might be a 10% kind of thing too. That's an estimate we made from field measurements, and it evolves through the season too. Maybe a two-dimensional model is a minimum that would resolve that. And I'm going to try. My colleagues are pushing me to try and improve this a little bit to do that, but I spend all the time I get paid on already, so I'm not sure that I'll be able to do it. But
so I'm really intrigued about those 4 points that didn't lie on your line.
yeah, me too.
Do you have any idea at all about what those could be?
I can tell you what doesn't work, because I was late by about 6 months submitting the report on that, because once I did it, I was like, I can't let it go without trying to explain those times, right? So I looked at temperature anomalies and river flow anomalies, and I published, in 2008, I think, and Bob Rolson had published as well, suggestions that the wind direction and duration had an influence on the extent and duration of hypoxia. So I tried that, but I couldn't explain it. So it's a challenge for anybody who wants to try and do it before I did.
So they were 8 to 10 years apart, is that correct? Roughly?
Yeah, there
Is
was
there anything significant about 8 to 10 years?
Yeah, there's lots
Is
of
it El Nino?
there's lots of decadal scale. Everything correlates with North Atlantic oscillation, and there's like a paper where recently somebody published about the correlations with these things and climate signals, but they were pretty naive in the sense that it's a correlation statistically significant, and did they estimate the degrees of freedom adequately? Because we've got 5 anomalies, right? So that's like, if you got linear regression, you've got 3 degrees of freedom. So they found the correlation. I don't know.
Again, those anomalies, do they statistically, and because you can find a lot of biology in circulation maybe that would correlate. But statistically, are those the places where you have the largest excursions?
Well, let me, actually,
For example, you could calculate the coefficient of variation, which I don't think you have, and to see in those places whether the coefficient of variation goes up at those anomalies. That's just
well, yeah, the residuals in the fit against the nutrient load is clear. I mean, that's what I showed here. Here, right? So I'm not quite sure what you mean by coefficient of variation, but the probability that if that was true, the probability you get that was by chance is 0. Right? So if you assume that the way of thinking it, the way I think about it is, if you assume the model is correct and that the deviations from the model are due to random variations in error, right? Then you can calculate the probability of getting something like that is if you know the errors, right? That's what chi-squared measures. And the probability of these things, this being true and these things due to error is 0. That's what I mean by they're inherently inconsistent with the model. Now, one characteristic that maybe a hint to what causes them is that during those years, the pattern sort of looks like this. Like the anomaly occurs mostly on the north side of Land Sand. And the other thing I want to mention is like the station spacing along here is not great, you know. So it's the further, the bigger it gets, the bigger the error. But I tried to estimate what that is, and also the dependence of the area on the data is nonlinear, right? Because of the station spacing. So, for example, if you had a small, if this point here or here was like 0.1 higher or lower, if it was 3.1 instead of 3, right? Now it would be outside. It would be above the 3 level, and this whole area would be cut out of the area estimate. So the dependence of the area on the location of the spacing is pretty sensitive.
I'm not sure I got a yes or no answer. I guess what I'm trying to get at is that at the very beginning you mentioned that there are these oxygen excursions.
Oh,
and I'm wondering if those excursions, which could be captured by coefficient of variation measure, have anything to do with those deviations.
I haven't. Let's see. I haven't looked at buoy data and those years very carefully, so I can't say.
It would be worth calculating because that might be why your statistics. Because when you have big variation and you have temporal autocorrelation, that is the worst thing in the world to do statistics.
Right, but I think my uncertainty estimates are intended to try and assess how big an impact those excursions would have on the area estimate. That's sort of the point of the Monte Carlo simulation, was to try and allow variations to be incorporated in the estimate of the area uncertainty.
Understood. I think it would be worth it to look at those.
I'm happy to try and do that sometime. Right, but the other thing you could do is like we could look for patterns in temperature and discharge and wind. And I did a lot of those, but I did it in a rush, trying because my report was due, and I didn't know that those anomalies were really there until I had kind of completed the whole thing. Right, there's a lot of software development and analysis and thinking that led to this figure. Where is it? Oh, so before. Sorry about this. I want to get back to that because it is kind of a provocative thing here, right? So those are the things that are the challenge, is to understand why they're there.
All right, I think we're almost on. I do want to give a student, if there's a student that wants to ask a question. Yeah, we do have a student question.
I have a question also. Track with the geo measurements. I noticed that the increments between the groupings, or just like the name for each like grouping that you had. So like one was like 1 kilogram per liter, and then like one would be like 1.5, or those based on like biological like importances.
No, those were determined by people who in 1987 who designed the program. In fact, I tried the person who did the GIS work, to make these maps, like these ones, right? they decreed the contours that would be drawn and the colors that would be shown, and so I spent like an hour when I was preparing my report trying to replicate the colors that GIS does with MATLAB colors. And so the contour levels try to reflect consistency so that the people who are responsible for taking action, the consequence of this would have less resistance.
All right, thank you so much. There's a lot of pizza, I hope, today, much more than last night. So hopefully all of you will have enough. And let's thank the speaker one more time.
Thank you.